Introducing aPriori.
Hi everyone, my name is Mark Gormley and I am the product manager here at aPriori with responsibility for the cost models of our assembly processes. And today I'm going to give you a short presentation on the additions and improvements we've made to this process group with our 22.1 release earlier this year. So today we'll cover the introduction of the contact region GCD, which is a new geometric cost driver in the assembly process group, which detects where parts are in contact with each other. We'll have a look at how we've used these contact regions in 22.1 to improve our cycle time estimates for clamping, and then how we're also using the information they provide to give us some more mechanistic estimates for the adhesive bonding and the sealing operations. Then we'll have a look at some changes not related to contact regions. We've made some updates to our assembly load time logic based on feedback from customers, as well as our own customer success organization, who've let us know that this is a very commonly configured part of our logic. And finally, we'll have a look at some of the changes we've made to the welding cycle times. Again, very much driven by feedback we've had that this is a common area where our code is configured in our customers' own digital factories. We'll begin with the biggest change to the assembly process group for 22.1, which is the introduction of a new GCD, which we're calling contact regions. The purpose of these is to identify which parts in an assembly are in direct contact with each other and by how much. So a contact region is simply a single continuous area of contact between two parts, and then we further organize these into contact groups, where a contact group is a collection of all the contact regions between any two parts. So in this simple example, there are two contact regions between this triangular gusset and the L-shaped bracket, and the contact group is made up of both of these contact regions. And as well as identifying and highlighting the location of the contact regions, we also extract the area, the length, the width, and the perimeter of these. Now, as with any change of this nature, where we're gathering new information and creating new GCDs, there is a performance impact, and the GCD extraction for assemblies now does take a little bit longer. However, in most of our testing, this was just an extra few seconds of time for most of the assemblies that we tested. But if you find that in your environment, GCD extraction for assemblies has slowed down too much, and you are still using an existing configured digital factory, which doesn't yet make use of contact regions, we have put in a site variable to toggle their extraction. So this behavior and the extraction of these can be disabled if desired. A further distinction that we make is between contact regions which exist at different levels of the assembly. And this means that aPriori will respect the assembly tree structure as it exists in the CAD hierarchy. So any contact regions which are between the immediate children or the level 1 subcomponents of the assembly are considered to be top level contact regions, and places where parts are in contact with each other either within or between individual sub-assemblies are defined as lower level contact regions. So in this very simple example in the lower left, I have made it two instances of the same small, simple assembly together. So we have two identical sub-assemblies in this assembly. There's one top level contact region between them, highlighted here in the lower right image. And then, as you can see in the upper right image, everything else is determined to be a lower level contact region. Now, this might kind of sound superficial, but we do this to try and make better assumptions around how exactly assemblies are brought together. So by only applying assembly operations to top level contact regions, we can assume that the sub-assemblies are added in one piece, rather than built up by individually adding each of their own subcomponents in turn. So what this means for this example is that we consider the size, the weight, and the points of contact of the entire sub-assembly rather than the properties of its individual piece parts. And now this becomes very important for making assumptions around the clamping of welded sub-assemblies, which is what we'll be talking about on the next slide. But another reason we decided to make this distinction is simply one of user friendliness. So again, on this example assembly, we have 15 contact regions. On larger assemblies, which are more representative of real products, this can very typically get into the hundreds. So by adopting this philosophy that we work at the top assembly level, we make it much easier for the user to see how the assembly comes together, with the expectation that if we want to change something within one of the sub-assemblies, we can open that sub-assembly up in its own tab and make our changes there. So As mentioned previously, the major benefit of these contact regions is that we can now start to make more mechanistic assumptions when estimating cycle times and costs for assembly processes. And the first of these is clamping. Now, previously, clamping was automatically assigned to all subcomponents in an assembly if there was a weld or a bonding operation anywhere on that assembly. So as soon as a user added one weld, every subcomponent got a clamping operation. And likewise, as soon as one adhesive bonding operation was added to any part in the assembly, all of the parts in the assembly had clamping applied. Now, this assumption was arguably sound for welding, as most often we see the weldment modeled in its own level within the CAD assembly, in which case it's likely that everything would be clamped. But it's likely not as strong an assumption for bonding. We do see a lot of assemblies of a few dozen parts where maybe only a couple of them are bonded. So what happens now for welding is that clamping operations are automatically applied to contact grips whenever a weld is present on a contact region within that grip. So now, whenever a user applies a weld between two parts, we look at all the places where those two parts are in contact and we apply clamping to that grip. And as users go through the weldment and apply more welds, when they update the scenario by running it again, they'll see those parts then get clamping applied on top of the existing ones. So hopefully this helps illustrate the importance of what we were talking about on the previous slide regarding making the distinction between contact regions at the top level and at the lower level within the assembly. If we didn't do this, we'd just assume that individual piece parts are sort of clamped and then welded on individually. But by making this point of recognizing them in the way that we have, we can treat a very large sub-assembly as something which is maybe craned in, clamped and welded all on in one piece. Now, the cycle time for clamping previously was just a fixed time for each subcomponent, regardless of its size. But now we have a time per clamp and an estimated number of clamps based on the size of the contact region and an assumed spacing of the clamps themselves, which is 6 inches by default. But this can be updated by a digital factory manager. We'll also add in an extra clamp if we believe that it's required for extra stability for thin folded parts. And we determine this based on the ratio between the area of the contact region itself and its enclosing rectangle. So in this example here in the bottom right, if you can imagine the blue area being the contact region of the part as if it were sitting on the screen, we would add an extra clamp in for the example on the right, assuming that the blue area is less than 10% of the rectangle around it. We also try to account for whether the clamps are manually or automatically applied, so by using like pneumatic systems. There's a huge amount of variation now on when and where automatic clamps are used instead of manual, including variables like weld access, ergonomics, safety, production volume, and so on. So our simple assumption for now is to use manual clamps for manual welding processes and automatic clamps for robotic welding processes. But this can be overridden by end users in their scenarios directly, or these default assumptions can be changed by digital factory managers as well. For adhesive bonding and phase sealing, we now use the area of the contact region to estimate the cycle time. We have a degreasing rate and a bonding application rate in area per unit of time, so square millimeters per second or square inches per second. And then when we combine this with the area of the contact region, it gives us an estimate of the time required. Previously, the area to be bonded or sealed was an assumed percentage of 10% by default of the total surface area of the entire assembly, which the user was expected to override with an area that they could measure from their CAD program. So this functionality brings that step into aPriori itself, automates it, and as such, it represents a much more dependable way of estimating the cycle times for these operations. Okay, next up are some more general logic updates. So we've updated the component load time lookup table in the assembly process group to now hold information on the size of a part as well as its weight, whereas previously we just considered the weight of the part. We will also now differ the number of operators that are being used to load parts based on their size and their weight. So a relatively small but heavy part might get 2 operators, as will something like a large flat panel, which maybe isn't necessarily that heavy, but still requires more than 1 person to lift it. And for transparency, we've also got 2 columns in here about the type of equipment that we're assuming are being used for loading the parts. So for very small, light parts, we assume no equipment and that they're just assembled on by hand. up through 3 different levels, with level 1 being sort of unpowered lifting aids and harnesses, level 2 being small to medium powered lifting aids, and level 3 representing kind of very large devices such as overhead gantry cranes for the heaviest of parts and the largest of sub-assemblies. And this also shows where we make the distinction between something which can be loaded by hand versus something which will require a lifting aid, which is always about kind of 15 kilograms or 35 pounds based on the recommendations given by most countries' kind of health and safety / OSHA type agencies. So on this slide then is a quick example of how we actually take those individual load times and sum them up to give us the total amount that the user will see presented to them. So what happens is for each component, we pull the load time and the number of required operators from the table, multiply those two numbers together to get a total incurred labor time, and then we sum that result for all of the components. And then for unloading, we take the size and weight of the entire assembly, and we look that up in the same table. So previously, we just defaulted to one operator for the entire process, but now we might have different numbers of operators for different subcomponents. So we might have some very large heavy parts that require 3 people and an overhead crane, and then the rest of the parts might be very small, and we would assume that one individual operator would be able to handle those. And next up are some logic updates that we've made to the welding cycle time. We'll do that one again. Next up are some updates we've made to the welding cycles. Tech 3. Next up are some updates we've made to the welding cycle time logic. So we've added some Tech 4. Next up are some updates we've made to the welding cycle time logic. We've added in some time for the operator to reposition themselves while laying longer welds. And we do this by having a value which represents how far an operator will lay weld in one trigger pull with a default value of 6 inches. And then once welds are longer than that, we add in a gun placement time again to account for the operator having to stop welding, come off the workpiece, maybe check something, adjust something, clean something up, and then go back in, pull the trigger and start welding again. So once the weld is over 6 inches, we add that in, and then if it's longer than 12 inches, we add it in again. This value is a machine field, which is stored in the digital factory, so it can be changed by digital factory managers if required, if you want to update the assumption. We've also increased the value of that gun placement time based on its previous value of 12 seconds to 10 seconds. And this is based on feedback that it was a bit too low before and that we were underestimating the time. So the overall effect on cycle time can be summarized as being that any welds shorter than 6 inches will increase by 8 seconds because that initial gun placement time has gone from 2 seconds to 10 seconds. And then for any welds that are longer than 6 inches, they'll have a further 10 seconds added on for every 6 inches of their length. And finally, another addition to our welding processes is the addition of a process setup option, or PSO, which allows a user to specify a value for the number of times that an assembly is reorientated during the welding process itself. So we did investigate trying to estimate this automatically, but we felt that we really didn't have enough information to have a good go at it, and we would more often than not come up with the wrong answer. So it's clearer from a user perspective to default it to 0 and allow the user to add a value in based on their own judgment or input from a manufacturing engineer. And in the interest of keeping cycle time information together and reducing the number of places where a digital factory manager needs to maintain information, we've stored the value for the time itself in the same component load time table we were looking at earlier. And again, we're assuming a relationship between the size and weight of a weldment and the time that it takes to reorient or flip it over to give the operator access to the other side. So something like a small frame might be jigged up on a table, which the operator can unlock and rotate by hand. And at the other end of the scale, something like a truck chassis, which would be on a large motorized gimbal. So between the cycle time logic changes and the clamping changes that I talked about previously, some significant cycle time changes for welding and clamping with 22.1, but more mechanistic, more justifiable, and something which digital factory managers and end users have much more control over. So this concludes the updates that I have for you today. If you have any questions, please reach out to me via my email, which is on the screen right now. And of course, existing customers can reach out to their consultants or their customer success managers. Thank you very much and goodbye.
aPriori, making profitability and sustainability a reality for a better world.